Our universe is a vast and awe-inspiring place. Imagine a dark canvas stretching out infinitely, dotted with billions of stars. Each star, a fiery ball of gas, emits light and heat, illuminating the darkness. These stars cluster together to form galaxies, vast islands of light separated by enormous stretches of empty space. Our own galaxy, the Milky Way, is just one of billions in the observable universe. How did this universe, teeming with stars and galaxies, come to be? The answer lies in a theory known as the Big Bang. Imagine all the matter and energy in the universe compressed into a point smaller than an atom. This point, known as the singularity, is where our journey begins. It is a realm of extreme conditions, beyond our current understanding of physics. Time, as we perceive it, did not exist before the Big Bang. At the singularity, all the laws of physics as we know them break down. Gravity becomes infinitely strong, compressing everything into an infinitely small point. The very fabric of space-time is thought to have been incredibly curved, warped beyond recognition. However, it is from this enigmatic starting point that the universe, as we know it, sprang forth. The Big Bang was not an explosion in the conventional sense, but the expansion of space itself, an expansion that continues to this day. From the singularity, the universe began its rapid expansion, a period known as the Big Bang. In the first fraction of a second, the universe underwent an exponential growth spurt called inflation. This period of rapid expansion is crucial for explaining the universe's remarkable uniformity. Imagine a tiny, subatomic region of space suddenly expanding to billions of times its original size in a fraction of a second. During this epoch, the universe cooled dramatically, and the energy that drove inflation was converted into a sea of fundamental particles. This rapid expansion smoothed out any initial irregularities or bumps in the universe. The end of inflation marked a transition point in the early universe. The energy driving inflation decayed into a soup of fundamental particles, setting the stage for the formation of the first elements and eventually, the stars and galaxies. As the universe cooled after inflation, energy began to condense into matter, following Einstein's famous equation EMC2. This equation tells us that energy and matter are interchangeable. As the universe expanded and cooled, the energy density decreased, allowing for the formation of particles. The first particles to emerge were quarks, leptons, and their antimatter counterparts. Quarks are the fundamental building blocks of protons and neutrons, while leptons include electrons and neutrinos. These particles interacted with each other in a hot, dense soup, constantly colliding and annihilating in a flurry of energy. As the universe continued to cool, a crucial imbalance emerged between matter and antimatter. This asymmetry, though tiny, had profound consequences, as it ultimately led to the matter-dominated universe we observe today. As the universe cooled further, a pivotal event occurred: nucleosynthesis. During this period, roughly 3 minutes after the Big Bang, the universe was cool enough for protons and neutrons to combine and form the first atomic nuclei. The primary elements formed during Big Bang nucleosynthesis were hydrogen, helium, and trace amounts of lithium and beryllium. These light elements, forged in the crucible of the early universe, would later serve as the raw materials for the first stars and galaxies. This era of nucleosynthesis lasted for only a few minutes, but it had profound implications for the evolution of the universe. The abundance of hydrogen and helium, as predicted by Big Bang nucleosynthesis, is one of the key pieces of evidence supporting the Big Bang theory. These predictions closely match observations of the elemental composition of the universe. The formation of these light elements marked a crucial step in the evolution of the universe. For the next 380,000 years, the universe remained a hot, dense plasma of ionized hydrogen and helium. Light, constantly scattered by free electrons, could not travel freely. The universe was like a dense fog, opaque to electromagnetic radiation. However, as the universe continued to expand and cool, a profound change occurred: recombination. The temperature dropped to a point where electrons could combine with protons to form neutral hydrogen atoms. This transition marked a pivotal moment in cosmic history. With the formation of neutral hydrogen, the fog lifted and the universe became transparent to light. This first light, released when the universe was about 380,000 years old, is still detectable today as the cosmic microwave background radiation. The cosmic microwave background, or CMB, is a faint afterglow of the Big Bang, a thermal radiation that permeates all of space. It is a snapshot of the universe in its infancy, a time when it was just 380,000 years old. The CMB is like a cosmic time capsule, preserving information about the universe's conditions billions of years ago. Discovered in 1965, the CMB is one of the most compelling pieces of evidence supporting the Big Bang theory. Its existence and properties, such as its near-perfect blackbody spectrum and tiny temperature fluctuations, align remarkably well with theoretical predictions. These tiny temperature fluctuations in the CMB represent the seeds of density variations in the early universe. The CMB provides us with a glimpse into the universe's past, allowing us to study its earliest moments and understand its evolution. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery that revolutionized our understanding of the universe. By observing distant galaxies, he noticed that they were not stationary, but were moving away from us. Moreover, the farther away a galaxy was, the faster it seemed to be receding. This observation, known as Hubble's law, provided the first concrete evidence that the universe was expanding. Imagine dots on the surface of a balloon being inflated. As the balloon expands, all the dots move farther apart, with the more distant dots appearing to move faster. Hubble's law can be expressed mathematically as V equals h/d, where V is the recessional velocity of a galaxy, d is its distance from us, and h0 is a constant known as the Hubble constant. The discovery of Hubble's law was a watershed moment in cosmology, providing the first observational evidence supporting the Big Bang theory. While the Big Bang theory successfully explains many observed features of the universe, some mysteries remain. One of the most perplexing is the question of what caused the universe to inflate in the first place. Another puzzle is the nature of dark matter and dark energy. These mysterious components, which together make up about 95% of the universe's energy density, have profound gravitational effects on the evolution of the universe. Dark matter, which does not interact with light, reveals its presence through its gravitational influence on visible matter. Dark energy is thought to be responsible for the accelerated expansion of the universe observed in recent decades. Understanding the nature of dark matter and dark energy is one of the most significant challenges in modern cosmology. To probe the universe's earliest moments and address some of these mysteries, physicists have turned to theoretical frameworks like string theory. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. Imagine tiny, one-dimensional strings vibrating at different frequencies, much like the strings on a musical instrument. In string theory, these vibrations give rise to the different particles and forces we observe in nature. One intriguing aspect of string theory is that it requires the existence of extra spatial dimensions beyond the three we experience in our everyday lives. These extra dimensions are thought to be curled up or compactified, too small to be detected directly but potentially influencing the behavior of gravity and other fundamental forces. String theory also raises the possibility of a multiverse, a vast ensemble of universes, each with its own set of physical laws and constants. The Big Bang theory, with its description of the universe's origin and evolution, is a testament to the power of human curiosity and scientific inquiry. From the singularity to the formation of galaxies, the Big Bang provides a framework for understanding the cosmos and our place within it. However, the quest for understanding is far from over. Mysteries about the early universe, the nature of dark matter and dark energy, and the possibility of a multiverse continue to intrigue and inspire cosmologists. As we develop new technologies and refine our theoretical models, we can expect to uncover even more about the universe's origins and evolution. The journey of cosmic discovery is an ongoing one, filled with challenges and rewards, as we strive to comprehend the grand tapestry of the cosmos.